Hello everyone, this is Randall Pike and I'm going to be lecturing on section 7.1, which is orthogonal bases and orthogonal matrices. So let's get going. So the notions we're going to introduce here are orthogonality, which we know orthogonality, that's perpendicularity, and orthonormal bases, orthogonal and orthonormal bases. So two types of bases that are going to be very useful for us in our subsequent studies. So first of all, orthogonal, a set of vectors is orthogonal if their inner products are zero. Okay, so they're zero for I not equal to j. So they're pairwise orthogonal. So pairwise orthogonal. And an orthonormal basis is in addition to that, which is here. So this is the dot product being zero for I not equal to j. When I is equal to j, we have equal to 1. So this says that vi dot vi equals 1, but vi dot vi, as we know, is the norm of vi squared. And if that equals 1, then the norm is 1, okay? Since the norm is positive. So the norm of vi equals 1. So this is the notion of normed vector, okay? A vector that has norm 1. Norm equals 1. In addition to pairwise orthogonal. Okay, so it's a little bit more than just orthogonal bases, an orthogonal set of vectors. So we see from the definition that orthonormal basis is an orthogonal basis to begin with, is an orthogonal basis. It just has the added feature that the vectors have norm 1, okay? So for example, the standard bases are orthonormal. Okay, so the standard bases, which we've been denoting as E1, E2, etc., En, orthonormal bases. Orthonormal bases. For example, so in R3, we'd have 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so it's easy to see for the standard bases that they're pairwise orthogonal. The dot products is 0, pairwise, but the dot products with themselves are 1. Their norm is 1. Good. Now there's many other examples of bases that aren't, or that are not the standard bases. So in R2, we might take these vectors here. So here's 1 and here's 2. So V1 and V2. Okay, so in R2, I'll take V1 to be 1 over root 2, 1 over root 2, and I'll take V2 to be minus 1 over root 2, 1 over root 2. Okay, so we can see that V1 dot V2 is 0, and we see that the norm of V1 is 1 and the norm of V2 is 1. Okay, so there's an example in R2 of an orthonormal basis right here. So B equals V1, V2, orthonormal basis. That's not the standard one. Okay. So many consequences of having an orthogonal or an orthonormal basis. They're both very efficient computationally. So for example, here, orthogonality implies linear independence. Okay, so let's go through this list. So let's call that A. Okay, so A, So we suppose B is a set that is orthogonal. So let's go V1 to VK orthogonal. Gonal set. Doesn't have to be a basis. Okay, let's go and show that they're linearly independent. So suppose, as we always do when we start with the linear independence question, we look at this linear combination of the vectors and we set it equal to the 0 vector. Okay, now what we're going to do then is we're going to dot it this left hand side with a vector, let's call it Vj. So CK, yep, CK, VK. Then I'm going to pick one of the vectors and do the dot product, okay? Which means that on the right-hand side, I do the same thing. 0.vj is going to be 0, right? But when we do the left-hand side, we're going to get a sum like this. So C1 V1.vj plus C2, I'll draw one more, V2.vj. Now somewhere down the road, there'll be the jth vector. So let's put that one here. So Cj Vj.vj. And then you'll have the Cj plus 1 V, the next one in the list, dot Vj. And then finally to the end, Ck Vk dot Vj. And now this is all 0 as we've established. And then we go through each one of them and we see that all these terms are going to be 0 because of orthogonality. So all these ones here. Okay, so this is orthogonality, pairwise orthogonality. But one that remains here is not going to be 0. This one's going to be Cj times the norm of Vj squared. So I'm not assuming orthonormal, so this doesn't have to be 1. And on the right-hand side, we have 0. So there's Cj times a positive number that equals 0. The only way that can happen is Cj equals 0. So since this is true for all j, we have C1 and C2. We have all the C's equal to 0, the coefficients. And so B, I'm calling it B, is linearly independent. Okay, so it's a strong notion to be orthogonal, the set of vectors to be orthogonal. Okay, so orthogonality implies linear independence. Notice that if we have a basis that happens to be an orthogonal set 2, then we'll call it an orthogonal basis. So you'll see that from that term, it's a basis, meaning that it's linearly independent and it spans the set, the subspace, and that they're orthogonal. Now the last one here, let's call that C. An orthogonal set, then we have this kind of Pythagorean theorem here. Let me just write that down. So for C, which we can call the Pythagorean theorem in many dimensions. All right, and I should put that in brackets. So why is this true? So if I have the sum of an orthogonal set of vectors, so these are orthogonal vectors, v1 to vk, and I add them all up, and I look at the norm of that vector squared. All right, remember when you measure the norm of a vector squared, it's the dot product with itself, the vector with itself. Okay, so the norm of a vector, call it x squared, is x dot x. So if I want to compute the square of this, the norm of this vector, I can take the dot product with itself. So let's do that. So v1 plus v2 plus dot dot vk dotted with v1 plus v2 all the way up to vk. All right, now I'm going to use distribution of the dot product, right? So I'm going to get v1 dot v1, and then I'm going to have, as I continue distributing, the V1 across there, I'll have all that, and I'll have a bunch of terms. Then I'll come to the V2 part here, and I'll have the V2 dotted with the V1, but I'll also have the V2 dotted with the V2, etc. So you see what happens is that most terms will turn out to be zero, the ones where these guys will be zero when you don't have the indices being the same. But every once in a while, you'll have these ones where the indices are the same. Okay, so that's these guys here. And those are not zero. In fact, those are the norm squared. So the only terms left are going to be v1 dot v1, which is v1 squared. And then the next term that will appear, that's non-zero, will be the v2 norm squared. And then I'll get all the vectors coming out this way. So they're norm squared. Okay. So it's a kind of Pythagorean theorem because you're summing up perpendicular segments and looking at the line that joins them up, the norm squared. Okay. Now, these kinds of bases, orthogonal bases and orthonormal bases, are very convenient for us to use when we want to compute the coordinates of a vector relative to these bases. Okay, so for instance, we're talking about orthogonal bases. Okay, so let's set for S a subspace only. Okay, so we take a vector from the subspace, and then we find its coefficients with respect to that basis. So let's take a vector x in the set S. Okay, so S is a subspace, and V1 to Vk is a basis, but an orthogonal basis. Because it's a basis, I can write x as a linear combination of these vectors, so C1 V1 plus all the way up to k, Ck Vk. Okay, so that's due to the fact that the set of vectors v1 to vk is a basis for this subspace S. Now I'm going to take the dot product with a vector in the basis with this vector x. So I'll do vi dotted with x. All right, so now instead of writing x, I'm going to write its sum in the basis vectors. So here it is. All right, and then now I'm going to use distribution, distribute that dot product across here. The only thing that's going to remain is the ith term, so ci vi dotted with vi, which is ci vi norm squared. Okay, hence I solve for the ci in that equation, and I get this term right here. All right, so the CIs are easy to compute. I don't have to solve a system of equations. I just have to take dot products with basis vectors with the vector x I'm considering. So for example, let's consider this basis I had in R2. So a basis, an orthogonal basis, actually orthonormal basis. So I should make a remark here. Mark, if the basis is orthonormal, so that's a little bit more than orthogonal, then this formula is actually a little bit simpler because the norm of the v is 1, so it's just simply vi dotted with x. Okay, so that's the formula in an orthonormal basis, even simpler. And that's what we have here in this example. I'm going to take that example from the page above. So I'll take 1 over root 2. 1 over root 2 is my first basis vector. And the second basis vector minus 1 over root 2. 1 over root 2. 1 over root 2, 1 over root 2. Okay, so there's an orthonormal basis. And let's take v to be this vector here, 0, 2. Okay, so we have v can be expanded in this basis. So let's call this v1 and v2, the two basis vectors. So this vector v, or actually let me call it x like I did above there. So let me call it x here. So x equals that. And this will be my x again. So because x is in R2, then I can write it as C1 V1 plus C2 V2. and I have C1 according to our formula above. This is now an orthonormal basis, so C1 will be simply V1 dotted with X. Okay, now if you dot V1 with X, you're going to get 2 over root 2 with, V1, 2 over root 2, which is root 2. And C2 will be obtained by dotting X with V2. So when I take the dot product of V2 with X, I also get 2 over root 2, which I'll write as root 2. Okay, so that's our coordinates of X. So I could write X in basis B as coordinate vector root 2, root 2, which means X is equal to root 2 V1 plus root 2 V2. And if we make a little sketch here, we can see why that would be true. So there's my two basis vectors. Those are norm 1. Okay, and we have this X vector up here, which is somewhere near the top right here. There's my X. Okay, so we have, notice we're stretching the V1s and V2s a little bit. So the way you sum up to this vector here would be slightly increasing the lengths of V1 and V2 by a factor square root of 2. Okay, so that would be a parallelogram if I drew it more carefully, where X is at one is the diagonal line from the origin to X. Okay. Now, it is, so here's one example of why it's slightly more convenient to have an orthonormal basis over an orthogonal basis. So orthogonality, to begin with, was very useful here because it gave us simple ways to find coefficients of vectors in the span of the set of the orthogonal vectors just by taking dot products. But orthonormal bases just simplifies things a little bit because the norms of the vectors will be 1, so the many formulas that we will see will be slightly easier. Now, the hard work actually in finding orthogonal bases, which is what we'll do later in a lecture, is establishing that they're orthogonal, pairwise orthogonal. So that takes some time and some thinking to prepare bases like that. But once you have an orthogonal basis, then it's a simple matter to convert it into an orthonormal basis, which is what we're talking about now. Okay, so we call that normalizing an orthogonal base to an orthonormal base. All right, so let's take an example in 3 dimensions. So let's take a orthogonal basis in R3. Let's take this one. Now, you should get some experience with coming up with orthogonal bases yourself, and there's many ways to do it. One way would be to solve systems of equations. So you're trying to find vectors that are orthogonal to another set of orthogonal vectors, and then you can solve a system of equations to try to identify one of these vectors. So that's one way to do it, and that's probably what was done here to establish these vectors as being orthogonal. So let's check first orthogonality. Okay, so let me call this, let me call that V1, V2, and V3. So I have to take the pairwise dot products. So V1 dot V2, let's see what that is. That's going to be 2 minus 2 is 0. So far so good. V1 dotted with V3 is going to be 3 minus 6 plus 3. Also 0. And then the last pair is V2, V3. Okay, so V2, V3 will be 6 minus 6 equals 0. Okay, so they're pairwise orthogonal. This is what we mean by pairwise orthogonality. Okay, but let's ask, are they orthonormal? So remember, orthonormal means orthogonal plus normality. So they are orthogonal. So let's just check the norms now. Are the norms 1? Well, they don't look like it, do they? So the norm of V1 is the square root of 9 plus 2, looks like the square root of 11. And the norm of V2 looks like it's going to be the square root of 8. And the norm of V3 is the square root of 9 plus 8, so 17. Does that look right? Sorry, 9 plus 9 plus 4. Sorry, that's 22. Yeah, so I made a little mistake there. So let's do that. 22. And is V2? Yeah, 2028. Good. Good. So from this, we normalize. Okay, so now normalize. I'll make some space here. So now we normalize. Okay, so now notice I'm going to multiply these three vectors by scalar so that the norm of the new vector is 1. And I hope you notice that if I multiply vectors by scalars, I don't change their orthogonality. So as an aside, if x dot y equals 0, then ax dot by also equals 0. Okay, so if I have two vectors that are orthogonal, the x and the y here, scalar multiples of those vectors will also be orthogonal. So that's why I'm not concerned here. When I normalize these vectors, I'm going to multiply them by a certain scalar. I'm not concerned that that's going to ruin their pairwise orthogonality. They will still remain pairwise orthogonal, and you can check at the end that they are. Now, what are the numbers I should multiply these vectors by? Well, they're going to be 1 over the norms of these vectors. So I'm going to define a new set of vectors, u1, to be v1 over the norm of v1. Okay, so that makes u1 norm 1. And similarly for u2, I'll take v2 over the norm of v2. And for u3, I'll take v3 over the norm of v3. So what I obtain here then is a set of vectors u1, u2, u3, and now this is an orthonormal basis. Of R3. Okay, that's an orthonormal basis of R3. So now that we have an orthonormal basis, so let's call that, did we have a name up here? I didn't. So let's call this V1. Okay, so actually let's write it out. So U1 is going to be, where was it? Yeah. 1 over 11, right? Yeah. So it'd be 1 over 11. Did I have a minus sign here? Sorry. Yeah. Yeah. So U1 is 1 over root 11, 3 over root 11 minus 1 over root 11. U2 is going to be 1 over root 2, simplifying the square root of 8 a little bit, 0, 1 over root 2. And U3 will be, let's look at it again, yeah, 3 minus 2, sorry, 3 minus 2, right? Is that a minus 3? Let's see. No, that's a 3. Good, so let's do it. So 3 over root 22 minus 2 over root 22 minus 3 over root 22. Good. So if we did take a vector, w equals 1, 1, 1, we could write w as c1 u1 plus c2 u2 plus c3 u3, where c1, I wouldn't have to solve a system of equations. C1 would be w dotted with u1, c2 would be w dotted with u2, c3 would be w dotted with u3, okay? So these numbers, you can add them up. That's 3 over root 11, so w dotted with u1. So when I take the dot product with this w, I'm just adding up the components of the ui. So I'll get 2 over root 2 here, which is root 2. And then for C3, I'll get 3 minus 5, so minus 2 over root 22. Okay, so it's fairly easy to get the coordinates of vectors in an orthonormal basis, and almost as easy in an orthogonal basis. Okay, now we're on to another topic which does use orthogonality, okay, but in the context of matrices. So first of all, we're going to define what we mean by an orthogonal matrix. So don't get confused. This notion of orthogonality here applied to matrices is not talking about whether matrices are perpendicular to each other. No, it's not. It's another notion, but orthogonality does play a role in it, and it comes in with the sets of vectors that appear when we talk about matrices. We can talk about rows and columns of matrices. There will be some orthogonality appearing there. Okay, so first the definition. Notice it's a square matrix, so we're talking like in the context of determinants, we're talking about n by n matrices. It is orthogonal. When I take the transpose of that matrix, it's also a square matrix of the same size. So I can take the product, and the product A with AT makes sense. And that product is the identity. Okay. And when I see that formula, remember what we mean by the inverse? We mean that that matrix on the right here, AT, is its inverse. So also, let me just write it out in the other way. So you also have ATA equals the identity. All right. So either one of these formulas implies that the inverse of the matrix is in some sense right in front of you. It's just the transpose of the matrix. Remember, finding the inverse of a matrix is a lengthy procedure by hand. You have to row reduce the matrix to the identity and see what appears on the other side of that augmented matrix that we showed you the algorithm to do. So it can take some time. All right, but not for orthogonal matrices. And it's easy to check whether a matrix is orthogonal or not. You simply do this calculation, A with A transpose, and see whether you get the identity or not. So it's easy to check. All right, and as we'll see in this course, there's many uses for orthogonal matrices, and they often appear in applications of linear algebra. So the orthogonal matrices are a very important class of matrices in linear algebra and applied linear algebra. Okay, so some properties of orthogonal matrices, because they will be appearing quite a bit in the theory of linear algebra. Let's look at these properties A to E. Some examples I want to, some properties I want to remind you of the transpose, okay, because it's appearing here. So remember, if I take the transpose of a product of two matrices, I get the product of the transposes, but in the opposite order. So here A and B are just any n by n matrices of the same size. And also there's a relationship between the transpose and the inverse of a matrix. So if I take the inverse of the transpose of a matrix, it's the same as taking the inverse of the transpose. All right, you see how that switched those two superscripts? And we also want to remind ourselves how does inverses work with products. So the inverse of a product of two invertible matrices is the product of their inverses, but in the opposite order, just like we did when we took the transpose. We also have this property of the two properties of the determinant that are going to be useful here. So the determinant of a product turns out to be the product of the determinant, which looks rather mysterious, but it's true. And also, as I mentioned before, the determinant of the transpose of a matrix is the same as the determinant of the matrix. So there's some properties that we'll use to establish these properties of orthogonality up here. So let's go through them one by one. So let's read it carefully now. We're starting with a orthogonal matrix. All right. So that's our hypotheses. So statement A now is saying this other matrix, AT, it's also orthogonal. So on the face of it, that is something new here because we're just assuming A itself is orthogonal. AT, remember, is another matrix, a different matrix. Doesn't look like A typically. It's a different matrix. Is it orthogonal also? The answer is yes. Now, it is very easy to determine whether a matrix is orthogonal. Remember, all you have to do is multiply it against its transpose and see whether you get the identity matrix or not. So let's do this here. Someone comes to you and says, this matrix AT is orthogonal, and you challenge them. Okay, so I'm going to take that matrix, which is AT, and I'm going to multiply it against its transpose, which is ATT. Okay, so that's what you do. That's the first step you do. Someone gives you a matrix and they challenge you to check whether it's orthogonal. You simply take the product of that matrix with its transpose, and that's exactly what I did here. Now we have to use some of the hypotheses of the situation to see what this product turns out to be. So first of all, we'll use the property of the transpose, and you can recall that if I take the transpose of a transpose, I just get the matrix back again. Okay, so that's property of transpose. But now I have AT and A is orthogonal matrix. So I know this product is 1, okay? So first thing I did here was property of transpose. That's the double transpose. And this property right here was that A is orthogonal. I'm using the hypotheses. At some point I have to use that hypothesis, but along the way I may use some other properties like I did here. So that establishes A. Now B, okay, that maybe is a little more unobvious, less obvious. The inverse of this matrix A is orthogonal. Now the inverse is something that is a matrix that seems kind of far from A. In a sense, it doesn't really look like A, but let's establish that it itself is orthogonal. So we just sit down and we say, okay, there's the matrix given to me. I'm going to take its transpose and I'm going to look at that product. And I'm going to see whether it's equal to the identity or not. Okay, now we have to do something. So I'm going to use here one of these properties of the transpose with the inverse. Okay, and that's the second property right here. So I'm going to use property 2 here. Let's write 2 here. Okay, so that tells me that the transpose of an inverse of a matrix is the inverse of its transpose. So it's AT inverse. Okay, AT inverse. Now, A is orthogonal, okay, which means that its inverse is AT. So I'll write that on the side here. I'll write it in yellow because I'm highlighting some of my steps here. So I'm going to use the fact that A inverse is AT because A is orthogonal. So that's the first matrix here, A inverse on the left. I'm going to write AT instead. All right, so now what do we have? We have a matrix times its inverse, and that is the identity. Okay, so A inverse is also invertible. Sorry, is also orthogonal. Now the determinant, that's an interesting feature. The determinant of orthogonal matrix is 1 in absolute value, so it's plus or minus 1. So let's see how that works. We start with the identity. So that's the n by n identity matrix, and I know that determinant is 1. But I'm going to write the identity matrix as A times A inverse, right? So A is invertible. But for A inverse, I'm going to write AT. All right, so now I'm going to use some of these properties up here. So let me call this one property 3, the product property with of the determinant. So the determinant of A and AT is going to be the product of the determinant of A and the determinant of AT. Okay. And now I'm going to use another property of the determinant, number 4 here, which is the determinant of the transpose is the same as the determinant of A. So what I have here is the square of the determinant of A. So there we go. So we have the square of the determinant of A is 1, which means that the determinant of A must be plus or minus 1. Okay. What else do we have here? Yeah, D and E. So let's do those. So D and E are saying that the rows and the columns form an orthonormal set. That's very important. So D is the rows form an orthonormal set. Let me write it down here. Rows of A. Does it say P up there? It should say A. Yeah. Sorry. So let's just make a change here. So I'm going to actually white that out. So that should be A, and that should be A. Okay. So there's some corrections you guys can make in your notes here. That used to be P. It's A. We're referring to this orthogonal matrix A. So the rows and columns form an orthonormal set. So rows A form orthonormal set. Now, why is this true? Okay, so for the rows of the matrix, we're going to take the A times its transpose. So let's take A dot AT. So I know that's the identity. Okay. Now notice this is row of A dotted with column of AT, right? That's matrix multiplication. So if you look at the A dot AT ijth element, it's going to be ith row of A dotted with jth column of AT. Now, the jth column of AT, that's the transpose, that's the jth row of A. Okay, so now notice this is the identity matrix, right? So equals 0 if I not equal to j, and it equals 1 if I equals to j, right? Because that's what the identity matrix is. It has ones down the diagonal. So there it is. So that's establishing that the rows of A form an orthonormal set because the ijth element is just ith row dotted with jth row, ith row dotted with jth row. And those will be 0 if I is not j, and it'll be 1 if I equals to j. So that's how we prove that the rows are orthonormal. And for E, the columns are orthonormal. Columns A form orthonormal set. That's also easy to see, but now we go AT dotted with A, all right? And that equals the identity. And then you look at the ijth element here, and this is going to be, remember the dot product of the rows of AT dotted with the columns of A, which turns out to be the rows of AT are the columns of A dotted with. So it's the same kind of argument here, except you're working with columns now, okay? And then same as here, all right? So very interesting. Orthonormal matrices contain, as I was saying previously, it's rather laborious to come up with orthogonal or orthonormal bases, but orthogonal matrices supply you with two sets of orthonormal bases, one coming from the rows, one coming from the columns. So we will use that, and that is one of their uses is to provide us with orthonormal bases. Okay, so a sequence of equivalent statements. Okay, so one is A is orthogonal. Okay, so we have let's assume A is orthogonal. Let's look at a few of these. So if A is orthogonal, why is B true? So A implies B. Okay, A implies B. So let's look at B. So the norm of a vector AX. Okay, so I act on X with orthogonal matrix A. Remember, this is, recall, X, so norm of X, two things here, okay? So norm of X squared is X dot X, okay? And also, when I take the dot product of vectors, remember we're writing vectors as columns, so this is VT as matrix multiplication, it's V transpose times W. So dot product can be realized as matrix multiplication with the transpose. So this is what we're going to use here. So when I look at the norm of a vector. Let's take the square of it. Okay, so I know that that's ax dotted with ax. Okay, now I'm going to take the transpose of the first vector and multiply it by the second vector, multiply it onto the second matrix, I mean. So AT times AX. And then I use product of transpose, so that turns out to be XTAT multiplying AX. And now I have the A and AT together, which gives me the identity. And so I have X dot X, which is norm of X squared. Okay, so orthogonality means that, and then hence, because the norm is a positive number, I have AX. Norm of AX is the norm of X. So this is an important feature. A does not change the length of vectors. Lengths of vectors. Okay, so if you think about the geometric transformations in R2 and R3, transformations that don't change length of vectors. So you can start to list them off. There's rotations, reflections, right? And that's about it, rotations and reflections. The other kinds of transformations we looked at did change the lengths of vectors. So the orthogonal transformations are very special. So for example, rotations and reflections don't change. And actually, these are equivalent. B implies A also. And therefore, these are orthogonal transformations. Okay, orthogonal transformations. Okay. So a transformation that preserves length is an orthogonal transformation. That's A and B being equivalent. Now A and C, that's a little bit different. A implies C, say. So C is saying, let's look at it again. C is saying that the inner product is not changed when you multiply the vectors by A. So if I took two vectors x, y, and I looked at their dot product, that number is the same as the dot product of their images under A, AX and AY. Okay, so let's see why that's true. As under the assumption that A is orthogonal, so I look at this dot product, so AX dotted with AY, and again, I translate the dot product into matrix multiplication using the transpose. So now I see that as matrix multiplication. And then I use property of matrix, of transpose. And I'm going to use associativity here as I did above. I have this product of four matrices. I can choose which two to do first as long as I don't change the order. And I'll do the inner two first. So I'll have xt, I, y. Now I don't have to write the identity I there. So I have xt, y, which is just another way to write the dot product. Okay. So orthogonal matrices preserve dot product, and hence angle between vectors. That's also very important. Angles between vectors, because the angle between the vectors is given by the dot product. Okay, so remember that, recall, the cosine of that is x dot y over the norm of x, norm of y, and this will be the same as ax dotted ay, as we've just established, ax norm ay. You see that? So on the one hand, I have this one here, angle between x and y, that's theta. And here, this is telling me that theta is the angle between ax and ay, those two vectors, all right? So so orthogonal transformations are very rigid. They move things, but they don't distort things. Move them, but don't distort them. Another property is this. So D, we can kind of see why it's true. So the eigenvalues, real eigenvalues have norm, actually not have, but they are, right? So the real eigenvalues are plus or minus 1. They can't be anything else. And we can see why this is true. So vectors lengths are not changed by A, right? That was what we saw above. And if you think about eigenvalues, okay, if they're not 1, then the eigenvector is being changed. Its length is being changed. So if A doesn't have to, or the matrix A here doesn't have to have real eigenvalues, but if it does, they're plus or minus 1. And from this, we can also say, although it's not so obvious at the moment, but we can also say that complex eigenvalues have modulus 1, okay? All right, so all eigenvalues, real and complex, of A have absolute value 1. All right, absolute value is in terms of complex numbers is what we were calling the modulus, or you can still call it absolute value. Another statement here, let's see where it is. This last one here, let's go to this. Okay, so I'm going to call that star. Okay, so let's talk about star. Star says that if I take two orthogonal matrices, then the product is orthogonal. So that could have been something on the previous page because it's a property of orthogonality. But let's just do it here. So suppose A and B orthogonal. Okay. Question is the product orthogonal? All right, but now you know what to do. So if someone gives you a matrix, in this case it's AB, and they ask you, is it orthogonal? Then what you do is you multiply it against the transpose of that matrix. So there we go. And now I'm going to use property of the transpose, so that's BTAT. And now I'm going to use associativity of matrix multiplication. So I have this product of 4 matrices. I'm going to do the inner 2 first. All right, now B is orthogonal, so that becomes an I, which I can drop out now. And now A is orthogonal, so that becomes an I. Okay, and then similarly for the other product, for B times A. All right, so products of orthogonal matrices are also orthogonal. So that's it for this lecture. I'm going to log off now, and I'll see you next time.